In this module, we will learn how to write the equations of static equilibrium for a rigid body or other static mechanism in 2 dimensions. Notice that this will be an extension of our previous module D3 and the Acer's method. So it is clear from our study so far that if you have a body or a system in equilibrium, it must be true that the sum of all of the forces on that body must equal to 0. And I'll remind you that we know this is a vector equation. When you have a rigid body where now not all of the forces are concurrent through a given point, we also have another equation, which is that the sum of the moments of all forces and torques that act on that body or system must also be equal to 0. And that moment can be taken about any point that you like. So here's a schematic example. Here's a body which I'm drawing with 3 forces and an applied torque called M. And if you were to write the sum of the force equation abstractly, you have F1 plus F2 plus F3 equals 0. Notice that the moment M does not appear in the force equation. The other equation, the sum of the moments about P, well, first we have to choose a point P. You can choose any point you like, but once you choose that point, the sum of the moment about that point is equal to 0. And I'm going to illustrate this through what we know already about our process for making moments. So for example, if I take the force F1, I'm going to extend the line of action of that force. I'm then going to draw the perpendicular distance between that force and the point P and call that D1. And because I can see that that force makes a counterclockwise moment about P, I'll record that as a positive F1 times D1. With the second force, again, I'll extend the line through F2, construct the perpendicular distance to the point P. I notice that F2 makes a clockwise moment about P, so I get minus F2 times D2. And then with the third force, the same process, extend the line of action, draw the perpendicular distance, and then I see this force is making counterclockwise moment about P, so I add plus F3 times D3. And then with the moment, I just add M. I don't add M times anything. M is already a moment. Now, 2 quick points. One is, in many problems, you often do not know the value of D1, D2, or D3, so you have to use the other methods that we discussed. So my presentation here is somewhat abstract. In principle, there is a perpendicular distance, but in practice, you might be using a different method to calculate it. And the other thing I'll remind you is that the moment M, although it is drawn somewhere in the middle of this body, it creates a moment of the same magnitude in the same direction about the point P. That's what we learned about couples. Now, the standard form of these equations is to say, again, start with the sum of the force equation. And then in 2 dimensions, we have one equation for the sum of the force in X and another equation for the sum of the force in Y. Both of those equations independently add up to 0. And then in the moment equation, we have a scalar equation, and in 2 dimensions, the moment about P is thought to be a vector about the k-axis, but since there's only one k-axis, we'll call that a scalar equation. And so in total, this means we can solve for up to 3 unknown reactions with the 2-dimensional equations of static equilibrium, 2 force equations and 1 moment equation. Now, there are alternative ways of doing this. One is to say, let me write the force in the X or the force in the Y equation. And then what I'll do is I'll make the moment about the force, about the point P we initially had, but I can also pick another point called Q and write the sum of the moments about Q. And so in this system, I have 1 force equation and 2 moment equations. Another alternative is to say, let me not write any force equations. Let me now write 3 moment equations. So let's take the point P and Q, and I'll select the third point R, and I'll sum the moments about R also equals to 0. Now, the condition I need to maintain, however, is that P, Q, and R cannot all be on the same line, so I have to be careful about that. But as long as they're not all collinear, then I can have 3 independent moment equations. So in summary, in two-dimensional statics problems, you can write 3 equations and therefore solve for 3 unknown reactions. Let me make one final comment. You might still ask though, can't you keep writing more moment equations? Like let me give a point S and T and U and V and maybe even a million equations. I can always make another moment equation, right? You can do this, but let me just suffice it for now and say no matter how many of those equations you write, only 3 will be independent. And again, therefore in statics, you can solve for up to 3 unknown reactions per body.